threshold to get started. It is my pleasure to introduce Katie Klymko. She has worked on many different things in her career. She did her PhD at UC Berkeley, where she worked on statistical mechanics of non-equilibrium system and used different both computational analytical techniques to analyze different problems. And then she has been a postdoc at LBNL from 2018 to 2021, and she worked on very hard problems like fluctuating hydrodynamics and finite volume methods for modeling mesoscale systems, so she can solve hard things. And lately she has drifted to our end of the woods and is been working on different aspects of quantum algorithms, and she's been a NERSC staff member since fall of last year. So the floor is yours, Katie. Take it away.
Thank you. I'll share my screen. Okay. Okay, yeah, thank you for letting me speak to you all today. Very happy to be here. So I'm going to talk about some work I did during my postdoc at Berkeley Lab. And it was really focused on trying to come up with efficient ways to calculate eigenvalues for molecular systems of interest on quantum hardware. And our paper covering most of what I'm going to tell you today just got published. So if you want some more details, feel free to look that up. And we have another one hopefully coming out soon with a student who worked with us over the summer, working out a bit more of the theory underlying a lot of the work I'm going to be telling you about today. Okay, so I'll just start by acknowledging some of the key people in this work. So Carlos was a grad student at Berkeley, in Brigitte Whaley's group. Yuji's a student at MIT right now who worked on quantum algorithms with us over the summer. Norm was actually the person who got me started on this project, and he's a staff scientist at NASA. And Bert, I was working in Bert's group when I started on this project, and he put a lot of work into helping us get it finished. So these are some of the key players in the work I'm going to tell you about today. And I guess the starting question, which many of you are probably interested in as well, is studying systems that are difficult to simulate classically. And I think the poster child often used for quantum computing is FOMOCO, right? So this is a bacterial protein that undergoes, can catalyze this reaction, making ammonia from nitrogen at room temperatures and pressures, when we usually need to do it at very high temperatures and pressures. So getting a more detailed mechanistic understanding of what's going on here would in theory be very useful for society. But studying these types of systems classically very quickly becomes intractable because of the number of highly correlated electrons you need to have a grasp of. So really the question of, can we use quantum resources to study quantum systems that are classically intractable, is one that's of interest to many people, and in particular to get highly accurate picture of the energy landscape characterizing this reaction would be super useful. So that's sort of the high level, why do we want to be able to calculate something like energies using quantum computers? And of course, we're in this age where we don't have fully fault tolerant quantum hardware, and we probably won't for a while. And we have limited qubits, limited connectivity, and the circuit depths we're actually able to run and get out reasonable answers are quite short. So when it comes to algorithms that can work with those constraints and still get accurate values for energy eigenvalues, we have limited options. So in particular, I would say most people right now who are trying to answer these questions are focused on hybrid quantum classical approaches like variational quantum eigensolvers that use some combination of quantum resources and classical resources, because the other approaches that we know are quite good are just the circuits are far too long to be implementable on current hardware. So just a very short overview. Most of you probably are very familiar with how these types of algorithms work, but if you're not, the idea is we want to, say, calculate some ground state wave function. We want a good approximation to that. And we have a guess for how to set that up, a guess for the circuit we would need to apply to some initial state to get out an approximation for the ground state wave function. And the circuit has some parameters that we can optimize classically after we measure the energy. So this will have some onset structure that usually, people have a few different ones that they're looking at, like hardware efficient or UCC, but usually it's meant to be short depth enough that we can actually run on current quantum hardware. So then we prepare this state, measure the energy, and classically optimize these parameters and do this sort of loop until the energy reaches a minimum, which we know variationally it should be the best the lower it is. So this is sort of the normal structure for variational quantum algorithms. And this was sort of our starting point, but with the idea in mind that there had been these recently proposed non-orthogonal variational quantum eigensolver methods. And these types of methods look like the following. So they increase the flexibility of this ground state wave function guess by using a linear combination of these independently parameterized wave functions that each have a compact quantum circuit description. And we refer to these expansion states, we refer to these independent wave functions as expansion states. So the way this works is that using these expansion states, you can measure Hamiltonian and overlap matrix elements on your quantum device. And then you get out, by applying the variational principle to these coefficients C, this generalized eigenvalue equation. And this is a generalized eigenvalue equation instead of just a standard eigenvalue equation, because these expansion states that we're using as our ansatz are non-orthogonal. So sometimes this is confusing when I talk about it. The only thing that makes this non-orthogonal is that these expansion states have some overlap with each other. So instead of this being the identity matrix, which it would be in a standard eigenvalue equation, we have to deal with this overlap matrix. And then, as follows in normal VQE, you just can optimize the parameters characterizing these expansion states and continue the cycle until you minimize the energy. So this was work proposed actually from Berkeley, from Brigitte Whaley's group. And our question was really, what is the best method to generate these expansion states? This looks like a promising new formulation of VQE. But can we really optimize the types of expansion states being used? And we wanted the expansion states, we wanted them to be easy to prepare on quantum hardware. We wanted them to be sort of a natural description for the eigenstates of interest, usually the ground and first excited states that we want to calculate using these types of methods. And we also wanted to avoid optimization, because people who work in this field know that often optimization of these parameters can become the hardest part of the problem and make them classically intractable. So we wanted to kind of get away from as much optimization as possible. So the idea we settled on was to use time evolution to generate these expansion states. So we have some initial reference state, and we apply a time evolution operator to generate these expansion states. And you can imagine doing this in real time or imaginary time. So when we do this in imaginary time, you would just apply this time evolution operator multiple times to your starting state. Each time you apply it, you get a different expansion state that you can add to your generalized eigenvalue equation and get a better description of the energies of interest. And I think many people at the AQT are actually familiar with some methods related to this, like kite. because you've had some very nice papers come out actually implementing this. And imaginary time evolution in theory is actually a really nice way to target the ground state, because when you have imaginary time operator, it's basically a decaying exponential. And if your initial vector that your time evolving has any overlap with the ground state, you're eventually going to get to it by applying this operator enough times. But we actually wanted to avoid using imaginary time because it just often becomes very, very painful to implement, because it's a non-unitary operation and you need to play a bunch of tricks in order to get it to work efficiently. So we focused on the real-time axis, because the real-time evolution is unitary. So it's in theory natural for quantum hardware. So if we apply a real-time operator to our initial state enough times and generate this sort of basis of expansion states, that should in theory be much easier to implement. But maybe it's less obvious why that should be a natural basis to target ground and excited state energies. But I'll talk about why it actually turns out to be very natural using what we call this phase cancellation picture. And we term methods that use the real-time axis to target.
You apply those unitary operators in a classical computer?
No, quantum.
No, quantum. Yeah. Okay. Okay.
Yeah,
so you do it in an actual device.
Yeah, actual device.
Okay.
Yeah, and I'll step through on the next slide, I believe, the actual steps of the algorithm if it's not clear yet. But we'll generate this basis of real-time evolved states and use that to calculate our eigenstates of interest. And so we call these methods that utilize this type of real-time evolution variational quantum phase estimation, and that's because they have properties of both quantum phase estimation, which is one of the standard textbook methods for calculating energy eigenstates, and also variational quantum eigensolvers, which is the near-term version. So let me step through the methods just so it's clear. So we start with some reference state that we're going to time evolve, and ideally we want a reference state to have high overlap with whatever eigenstates we're interested in. So a lot of the examples I'll be showing you are quantum chemistry examples, so molecular systems. And for those systems, we know from our classical knowledge that something like a Hartree-Fock state is a really good starting state. It's a really good mean field description of the ground state. So in general, it will have high overlap with the ground state of the system, even if it's not exact. So for molecular systems, Hartree-Fock, it's easy to prepare, and it usually has high overlap with the low-lying energy states for the molecule. So we have our reference starting state. So then we apply on quantum hardware the time evolution operator to our starting state to get out a basis state. And we do this, so we're going to basically generate a state and then do a classical step and repeat the loop as many to converge. So in theory, we'll just apply it once, get out the first expansion state, and then with whatever expansion states we have, we can measure the Hamiltonian and overlap matrix elements on quantum hardware. And that results in this generalized eigenvalue equation, which we solve classically. So we've measured the matrix elements on quantum hardware, and then we solve for the eigenvalues classically. And we repeat, going back to step 2, for as many time evolved states as we need to add in order to get this this generalized eigenvalue equation. The energies that come out to converge to usually chemical accuracy is what we're looking for molecular systems. So is that clear, sort of the steps? We add as many time evolved states as we need to in order for convergence, but this is a loop where we generate a state on quantum hardware, we measure these elements on the quantum hardware, and then do the classical calculation and keep building up this matrix as many times as we need to. So hopefully that's clear, and if not, definitely ask me questions, but this is sort of the basic set of steps we're using. And the only parameter here that we actually need to optimize, in contrast to your traditional VQE methods, is the time step we're using. to evolve these states. Okay, so then the question, so I'll show you proof in a little bit of how this actually works, and it turns out it works quite well to get ground states for interesting molecular systems. And the reason it does work well becomes clear when we write out the reference state and the time evolved state and the basis of Hamiltonian eigenstates. So here we've done this. So this is our starting state, and these are our Hamiltonian eigenstates. These are the coefficients characterizing the starting state. And every time we generate an expansion state, we're applying this unitary operator. We're conserving energy, unlike what you would do in kite. So you're just adding this phase rotation to the Hamiltonian eigenstates in your initial vector. And then when we write it like that, it becomes clear that we should be able to make linear combinations of these expansion states that we've generated, such that these different phases cancel out targeted components in this initial state, so that we should be able to get access to all of the eigenstates contained in this reference state that have a high enough coefficient characterizing them. And in theory, what we're doing is really measuring an autocorrelation function by doing this. So this is just to give some intuition as to why, even though we're not, changing the energy as you would in applying something like imaginary time evolution, you're just rotating these phases. That should provide a good basis to target all eigenstates contained within your initial vector. And the only choice we have to make is how exactly to choose the time evolution grid that we're using to generate these states, because we can choose it well in such a way that we get a nice cancellation of phases. And for simple enough systems, we can define exactly the conditions we need in order to cancel the phases perfectly and extract everything we want from the initial vector. And I'll show you, so this is an equation that defines what we call these phase cancellation conditions and gives us, for spectra that we know and are simple enough, a formula to calculate the ideal time step to get out all the information that was contained in that initial vector. And I'm showing you, for a simple example, how this looks. So this is a linear energy spectrum. So this is, the spectrum for a harmonic oscillator. And I'll just orient you with these plots because I'll be showing a few of them as the talk proceeds. So we're looking at the energy error as a function of added time steps. So each step on the x-axis, we're adding another time evolved state and increasing the size of our generalized eigenvalue equation. So we calculate a state on the quantum hardware and make our Hamiltonian and overlap matrix element measurements, and then solve a generalized eigenvalue equation at each step. And we're just increasing the time step that we've added. And this is showing for the first 4 eigenvalues in the spectrum convergence as a function of time step added. And in this case, for a simple spectrum, we can calculate the perfect time step we need to evolve to get everything out exactly from our initial vector. And here there were, I think, 16 eigenvalues contained in the initial vector. And once we've added 16 time evolved states, we get them all out perfectly, even though I'm only showing you convergence of the first 4 eigenstates. So this is the energy error. We want it to be low. That means we have a very good approximation of the energy eigenstates, and you see they're decreasing as we add more and more states. And this is this inset is just like a geometric picture of what's actually happening. And it's looking at the phases as we add these time evolved states. And when we've chosen the perfect time step defined by this formula, they all cancel each other out. And this is in contrast, we could have chosen other time steps to time evolve our system, which I'm showing on the left. And you see the convergence in most cases is much worse. It's slower to converge these energy eigenstates. In some cases, the lower energies will actually converge faster, but the convergence of the entire spectrum is really optimal when we've chosen this time step. So hopefully these types of plots are clear, because I'll show them. Everything I've shown so far is for a model system, a harmonic spectrum, because we can do things analytically there. but now we'll start looking at actual molecular examples where we want to be able to estimate energy eigenstates for the ground state and the first excited states. Okay, so lithium hydride, it's a molecular system, not particularly complicated, but a good system to sort of like take a first stab at how we choose the optimal time step in molecular systems. So this is the same type of plot where we're looking at the convergence of the ground state energy as a function of real time step added to the generalized eigenvalue equation. And here we've just chosen a particular time step at random, because for a complicated system, we can't necessarily solve the equation I showed you on the previous slide, especially if we don't a priori know the spectrum. And the goal, like I mentioned earlier, for molecular systems is always to get below chemical accuracy, because that's what we can actually measure in experiments. So you see, when we do this time evolution for this type of molecule, we get this step-like behavior, which is kind of characteristic in these systems. If you've chosen a time step that's maybe too small, and what it means is that each time step that we're adding to the system is not actually adding any new information, because there's some noise in these systems. It could be the case that if you rotate if you apply too small of a time step, the new state that you've added looks too much like the previous states you've had, and only when we rotate far enough do we get an actual jump in information that we have about the ground state energy. So we use this feature, this sort of step-like pattern, to actually choose optimal time steps that are one optimizable parameter in this type of algorithm. So we use the step-like parameter to choose what an optimal time step for a molecule should look like. So if we go to a slightly larger time step size, you see that this step-like behavior starts to disappear, and that's because each new time step we've added is linearly independent from the previous one. So we're getting new information from each added time step. And likewise for a larger time step, until finally, even with like 3 time steps, you have a lot of new information. So that means, what does that actually mean for us? So the dashed lines are showing convergence of the first excited state, because we can get that out of this algorithm as well. So our sort of recipe for determining what optimal time steps should be for this algorithm are the following. We want to get rid of this step-like independence, because that means we're adding information that is redundant. But we also want to minimize the number of time steps we actually have to use, because doing time evolution can be expensive on quantum hardware. We want to minimize the actual number of steps we have to take. So in practice, what we've done for the molecules we've looked at is to choose the smallest time step, such that you lose the step-like behavior, but also minimize the total time you actually run the circuit for. So this is just an example of like sort of how we heuristically optimize the time steps we actually take to generate these expansion states. One other thing I'll mention, because it actually is important, right? Since we're actually trying to measure things on quantum hardware, noise becomes important in these systems, right? Any measurement we make of these matrix elements will by necessity be noisy, because of the hardware we currently have access to. And the way we deal with that in our systems is to do a singular value decomposition of this overlap matrix, basically throwing away any of the noisy values that we get. And we can choose the amount of noise that we discard when solving this generalized eigenvalue equation by choosing the singular value decomposition threshold. And one thing to note is that we're trying to show that we need a very small number of time evolved steps to reach chemical accuracy, because we want to do the minimum amount of work on quantum hardware as possible, right? Because we don't have a ton of resources right now. But the more noise we have, as probably makes sense, the more time steps we actually need to take, which is what this plot is trying to show. So this threshold, the amount we're throwing away when we do this decomposition, is a proxy for increasing noise in the system. So the noisier our system is, the more information we need to collect in order to get convergence to chemical accuracy for these systems. So that's just one thing to note. And at the end of the talk, I'll show you some very small results from quantum hardware where we had to use relatively high SVD thresholds, but it actually is enough to deal with the majority of the noise that we had from hardware. Okay, one other thing I'll say before I show you some of our molecular examples is that, I've mentioned that we have to choose some starting state in order to time evolve, which has overlap with our eigenstates of interest, usually the Hartree-Fock. It's beneficial to have a small support space. And by that, I mean, if we decompose this initial vector into the sum of Hamiltonian eigenstates with some coefficient, we would prefer, if we're targeting maybe the first 3 eigenvalues, for the coefficients to be large on those 3 eigenvalues and small on the rest of Hilbert space. So visually, like if we can start with a reference state that we're going to time evolve that only has what we call support on a small amount of Hilbert space, that will make our convergence way faster, right? And so this is probably not a foreign concept, that if we can, I think this is common in normal VQE as well, if you can start from an initial state that really has a lot of overlap with your eigenvalues of interest, you're going to perform much better. So again, Hartree-Fock, which is a mean field approximation to the ground state, turns out to work quite well for these systems. Okay, so what I'm showing you here is our results, which we've run. These are still classical results because they're still a bit too large for a range of molecular systems where we look at the ground state energy error as a function of time evolved state that we've added to the system. So these molecules range in complexity. Some are quite simple. Chromium-2 is one of the harder examples that we've looked at. And until like a few years ago, there actually weren't great classical methods to solve for the ground state energy for chromium-2. So I'll just make that, this is a relatively hard molecule to solve classically. And what you see here is that for all of these systems, you get relatively quick convergence. So I'm showing you the total time evolved, which is whatever delta t we're using times the number of time steps. But in all of these cases, we need on order 30 time evolved states max in order to get chemical accuracy. That means we need very few time evolved states to actually get a very good approximation of the ground state energy, which is quite compact if you compare it to other methods that you might use to get access to this information. And I'll just have a little inset that it doesn't work quite as well, but you can also using this method, get access to excited state convergence. And again, in all of these cases, we started from the Hartree-Fock initial state. So it turns out that for molecular systems, just having an initial state that's Hartree-Fock and using something like real-time evolution can provide a very compact description of the ground state wave function. So I mentioned that, for some of these systems, they range in difficulty classically. And I want to show you some proof of that. So here we're comparing the number of parameters we need in order to reach chemical accuracy. So for this method, variational quantum phase estimation that I've introduced to you in this talk, that means the number of time evolved states that we need to add in order to get to chemical accuracy. And we're comparing that to one classical state-of-the-art method, which is called ASCII, Adaptive Sampling Configuration Interaction. And ASCII basically will do a search for the most important determinants characterizing the wave function and include that in the description of the wave function. So to note, and this is just these two different colors for our algorithm, just indicate different levels of noise we're assuming in the system. So again, with larger levels of noise, we need to include more time evolved states. So this is a comparison of the number of states we need to converge a classical versus our quantum algorithm. And the most notable comparison is in this chromium-2 molecule, which is definitely the hardest molecule we've looked at and the hardest molecule in this chart. But what you should take from this is that the classical method needs orders of magnitude more variational parameters in order to converge the ground state to chemical accuracy compared to this method that we've introduced based on time evolution. So this is quite compact compared to what you would do with a state-of-the-art classical method. So we think we're doing pretty well. And I'll just note one other thing. So, you know, these are actually systems that I'm showing you that we've only run classically because they're just too big to implement on the quantum hardware I've had access to. And one thing you might ask is chromium-2, it's a very large system, and we're only including a subset of the number of determinants needed to describe the full system when we make these results. But when we've done system size scaling, so looking from including 1,000 determinants to describe the system to 1,000,000, the results really don't change that much. So just to convince you that this is not an artifact of using some smaller size description of the system. Okay, so what I've shown you so far is some evidence that this algorithm, which we call variational quantum phase estimation, provides pretty quick convergence for the ground state energy for some molecules of interest. And that's interesting, but we had a further development of this algorithm, which we call the unitary formulation of variational quantum phase estimation, which I'll describe on this slide. So we do the following. We take our original generalized eigenvalue equation and substitute the Hamiltonian operator for the time evolution operator. And so now we have a different equation, right? But it's isospectral with the original generalized eigenvalue equation. So we're going to get out the same eigenvalues. But it has some benefits. So now we're no longer solving for the eigenvalues of a Hermitian operator, but for a unitary operator. And if we write out what the matrix elements actually look like, we see the following. So the matrix elements of this time evolution operator, they look like an autocorrelation function, which we mentioned earlier. That's actually what we're measuring here. But furthermore, they have this really nice structure, because they're actually just a shifted version of the overlap matrix, which is on the right-hand side of the equation. And the overlap matrix has this really nice property. It has this toplet structure, which means that every row in the matrix is just a shifted version of the previous row. So this is a very nice property, because it means now instead of having to actually measure, as we would in the original generalized eigenvalue equation, n squared Hamiltonian matrix elements and n squared overlap matrix elements, we only need to measure n overlap matrix elements. So we've reduced the number of measurements we need to make from quadratic to linear, which in actually implementing this was quite helpful. And one other thing I should note is that the structure, which now saves us from making n squared measurements, it actually survives trotterization. So if we want to implement time evolution to generate these expansion states using time evolution, using trotterized time evolution, this toplet structure remains, meaning we need to make we're able to make these far fewer measurements than we would have if we were using this original generalized eigenvalue equation. So in practice, this unitary formulation is what we've been exploring, because we think it's more beneficial. So then the question is, if you're interested in actually implementing this type of thing on quantum hardware, how do you do it? And the main thing we need to do, given this simplification, is just measure this overlap matrix element. And this is something you need to do in many quantum chemistry applications anyway. If you want to try and do like quantum Monte Carlo on a quantum computer, you need access to the overlap matrix. So there are well-known methods to do it, one of which is the Hadamard test, where you do some controlled time evolution and measure X and Y, and you get access to the real and imaginary components of this overlap matrix. So we did actually implement this, but I'll say that doing, arbitrary controlled unitary evolution is actually quite difficult. The circuits can become quite long. And in practice, how we did it was to borrow tools from Costin and Ed and use the Berkeley quantum synthesis toolkit. So we had our unitary matrices that we could just use their synthesis tools to make as have as few C naughts as possible. And in practice, that's what we used before running these on quantum hardware. And this is showing this running this on IBM's CHASM simulator for a 10+1 qubit system for the transverse field Ising model. And in particular, I'll point out that Lindsay Bassman had a bunch of simplifications for running, setting up circuits with the transverse field Ising model, which some of you are probably familiar with. So we were able to run these quite efficiently on quantum hardware. So this is looking at energy convergence, ground state energy convergence in a 2+1 qubit system where the +1 is the ancilla qubit, and a 3+1 qubit system, where again, the +1 is the ancilla qubit. And the results aren't amazing, but they actually look quite clean if you compare them to some other ground state energy estimations that people have looked at. So we were actually quite happy with them. So these are our implementations using this controlled unitary operator to calculate the overlap matrix, the Hadamard test. Okay, so I have a few conclusions here that I want to point out, and then I'll take some questions. So what I hope I convinced you of here is that real-time evolution is actually a pretty good way to go if you have a decent starting state to calculate ground and excited state energies. It's easier to implement than imaginary time evolution. And actually, if you use the space cancellation picture, it provides a very intuitive understanding of why it should cause good convergence for the ground and excited states. And for the systems I showed you, in particular chromium-2, we need a very small number of time evolved states. We need to do a very little amount of work to actually reach chemical accuracy, which is ideal given current limitations on quantum hardware. So we expect algorithms like this. We hope that they will be powerful in the near term regime, and in particular with the formulation that we've found, this unitary formulation where we only need a linear number of measurements instead of a quadratic number, and we can utilize the Toeplitz structure of this matrix. We hope that it will also lead to easy implementation with very few measurements. And finally, I wanted to point out that these ideas are not completely new. This was brought up in the classical literature for classical filter diagonalization methods, which has a lot of similarities, where time evolution could be used to solve for static properties. But doing time evolution classically obviously becomes intractable quite quickly, which is why they never really got much traction, because they weren't going to be efficient methods. But combining that with actually doing more efficient time evolution on quantum hardware should make these types of methods actually quite powerful. So I should flash funding acknowledgements. We had a number of people work from different agencies, so thank you for the support. And I'll just also say future directions. We have a paper coming out with one of our students who dug into the theory a bit more and was tried to provide a few convergence properties for why we think this should work so well, and under what circumstances, what should the spectra look like that actually work well here, and how do we optimize the time steps we use. And further variations using a type of iterative approach to get even better convergence for the types of energies we're looking at. We also are working on further optimizing the number of measurements we actually need to take. It turns out that not all matrix elements of the overlap matrix are equally important. Some of them need to be sampled quite well, and some of them don't. So optimizing that is something we've worked on a little bit. And finally, I mentioned at the end, right, when we actually do this on quantum hardware, I used the Hadamard test originally because I thought that was the standard way to calculate overlap matrices. But it requires doing this controlled time evolution, which can become messy quickly as the systems grow bigger and more complicated. And we're working on more efficient ways to measure the overlap matrix, one of which that has been proposed is using shadow tomography. The Google group recently used this in their quantum Monte Carlo paper. So this is something we would actually like to try and implement this at a larger scale for more complicated systems. Okay, so that's all I had, and I'm happy to take any questions if anything was unclear. And thank you for the time. Okay, Philip Thomas, the methods that you describe have some similarities to algorithms that have come out of Tucker Carrington's group in recent years. But in that context, the focus is on computing vibrational eigenstates and not on running on quantum hardware. So I wondered, do you think it would be feasible to apply your ideas to computing vibrational spectra of molecules on quantum hardware? I'll answer naively that I don't see why not. I think that should be possible in theory, though I don't know if there's going to be extra complications that I would have to consider.
I guess just to add to that question a bit, I know next to nothing about quantum hardware, but
okay.
This sort of my background is, computing vibrational spectra, and the main complication I can imagine is that these problems are very high dimensional, but you're usually looking for a few eigenstates near the bottom of the spectrum, and so sure. I guess I'm curious at how well quantum hardware would explore, a high dimensional space like this.
So these methods in our direction, our mind, we're also, we were targeting the ground state and the first few excited states. In theory, this should work for other parts of the spectrum too. It would just, you might have to change the starting state, right? You need something with high enough overlap with whatever eigenstates you're interested in. And then if you have that, this should work. But for molecular systems, right, we know Hartree-Fock is a great starting point. For other types of eigenvalues, you could use this 100% if you have any overlap with them. It just will likely take a lot more time steps to actually get convergence to chemical accuracy. So you just need to start with some overlap. But then if, usually Hartree-Fock, you have like 99% accuracy with simple systems. Maybe it's less for highly correlated systems. So I would expect the convergence to be not quite as quick if you don't have that high level of overlap. Any other questions? Oh, question in the chat. Oh, thanks.
Maybe one question. So when you're coming up with these basis states, I forget what you call them, but the ones where you know, time evolved by certain amounts of time. What if those were derived by just like kind of random evolution? In the limit of going to like super many of them, I assume you could also converge the right energy, but we're saying
So
that because you're specially choosing these to be time evolved at different time steps, this will mean you'll need far fewer of them.
So no, it's an interesting question. Well, it should work for sure if you just choose random time evolved states and include enough of them in your generalized eigenvalue equation. One thing that we'll break down is this structure. So this unitary formulation depends on a linear time grid spacing. So that's something that we know for sure. But it's also true that you could definitely do it from what you're saying. Just choose a random set of time evolved states that are real time evolved, and you should be able to converge using this original formulation, the energy. I'm just not sure how exactly it would affect the convergence properties. There are better time steps than others for sure. And there's some, there are some like diabolical time steps, like if you choose a multiple of 2 pi, you're like rotating around the unit circle. So it would definitely work. It's just, I'm not sure how efficiently.
Okay, and then also, so there's like some kind of more optimal time steps than others. I assume this depends on the reference state you choose, right? If you chose a different reference state, the time step might be different. Or the optimal time step might be different.
I'm not actually sure, but probably. It definitely depends on the spectrum. So if it depends just on, forgetting at the ground state, it's going to be like, I think the gap to some degree, related to the gap between the ground state and the first excited state. So I think it depends more on the spectrum than exactly the starting state. But I'm actually not sure.
Okay. Yeah, I was just wondering if the optimal time step had some, I don't know, inherent relationship to the system itself, or if it was, I don't know,
it's definitely
to the
related to the system itself. Yeah. Any other questions?
And if there are no other questions, I think we should also thank Katie for an excellent talk.
Thanks, Robbie.
Thank you very much.
Thank you.